So let's learn how to tackle half-life problems when we have a fractional number of half-lives. Not one half-life, not two half-lives, but maybe 2.7 half-lives. And to do this, we're going to need to use a simple equation, final equals initial times 1/2 raised to the n. Let's take a look. Why is this necessary? Half-life problems with whole numbers of half-lives are simple. For example, if I ask what percent of cobalt-60 atoms will remain after 3 half-lives, it's very easy. We start at 100%. After 1 half-life, we're down to 50%. After the second half-life, we're at 25. After the third half-life, we're down to 12.5. And we have our answer very simple because it's a whole number of half-lives. But what about a problem like this? If we have a half-life problem with a fractional number of half-lives, they're just not as easy. For example, instead of exactly 3 half-lives, what if the question had said 3.52 half-lives? Well, we're going to need to use the equation because it just won't work to do it the same way we did before. There's the third half-life, 12.5%. But how do we do a 0.52 of a half-life? We can't use this simple method for this situation where we have a fractional number. So there's an equation. It's pretty simple. Final equals initial times 1/2 raised to the n. And this is basically multiplying by 1/2 however many times we need to. So it's, in a way, it's like final equals initial times 1/2 times 1/2 times 1/2 times 0.52 of a 1/2. And the only way you can do it is with an equation. There are other equations for half-life, so don't think that this is the only equation, but it is the simplest one in my opinion. So let's try an example where we are solving for the final amount. Let's do this problem. What percent of cobalt-60 atoms should remain after 3.52 half-lives? So we're going to pull out our equation, final equals initial times 1/2 raised to the n. So we're going to start with 100%, and we're going to multiply that by 1/2 3.52 times. And we do that by raising 1/2 to the 3.52. And when you plug it into the calculator, it should look something like this. Be careful with the parentheses. 100 times parentheses 1/2 close parentheses raised to the caret button 3.52, and we get our answer. 8.71% should be left, which makes sense. It's a little less than the 12.5% that we had with exactly 3 half-lives. It's still more than the next half-life. If we had had 4, it would have been 6.25%. So we're somewhere in between 3 and 4, but you can't just eyeball it. You have to use the equation. Let's look at a different example where this time we solve for the initial. The half-life of carbon-14 is 5,730 years. This is how they do carbon dating to figure out how old a sample is if it used to be living, if it was organic matter. Anyway, if 2.34 grams of carbon-14 remain after 9,876 years, how many grams were present initially? So if we tried to divide, we see we don't have a whole number of half-lives. We are somewhere in between 1 half-life and 2 half-lives. So it is important that you do this first step and find out exactly how many half-lives have passed by dividing one into the other. Now we'll use the equation, final equals initial times 1/2 raised to the n. But we'll need to rearrange it just a little bit to solve for initial and get initial by itself. So when I rearrange, initial equals final divided by 1/2 raised to the n. Be careful with your parentheses when you type this in. So that's going to be the 2.34 grams that were left at the end divided by 1/2 raised to the 1.72. This is what it should look like in your calculator. And notice how I used an extra parentheses when I started the denominator. And we get our answer, which is 7.71 grams. And that's reasonable because 2.34 grams, 1 half-life before that, it was around 4.6. One half-life before that, it would have been around, I don't know, 9.2. So our answer is somewhere in between 9.2 and 4.6, which is what we would expect. This next example is the hardest type. If we need to solve for the number of half-lives, we're going to need to rearrange this equation for something tricky. So the half-life of hydrogen-3, also called tritium, is 12.33 years. How many years will it take 3 grams of tritium to decay to 0.371 grams of tritium? Well, here's our equation, final equals initial times 1/2 raised to the n. But in this problem, we need to solve for n. And since n is up there as an exponent, we need to do some algebra. So here's our equation. First, I'm going to move the initial to the other side. So final divided by initial equals 1/2 raised to the n. Now, the key to moving that exponent down is by taking the log of both sides. When I take the log of both sides, that n gets to come down and be multiplied. So now on the left, I've got the log of final over initial, which is just fine because I can do whatever I want to this equation as long as I do it to both sides. By taking the log of the right-hand side, notice how the exponent n was able to come down and be multiplied by log of 1/2. So this is how we reverse an exponent in this situation. And I'll remind you once again, there are other equations that can be used in this situation, but I'm not going to use them. We're going to focus on this equation. How do I get n by itself? I need to divide both sides by log of 1/2. So n is going to be the log of final over initial in the top, divided by the log of 1/2 in the denominator. There are other equations. I could simplify this differently. I'm not going to. I suggest that you memorize this equation, or if you find one that you like better, memorize that. That way you won't have to try to do this algebra in the middle of a quiz or a test. So, by the way, be sure to use lots of parentheses in the calculator and make sure you close them properly. Let's get back to our example. And we have rearranged that equation to be log of final over initial up in the top, divided by the log of 1/2. Let's plug in our numbers. So in the top is going to be log of 0.371 over 3. Make sure it's final over initial and not initial over final. And then I'm going to divide all of that by log of 1/2. So we see log of our 0.371 over 3 in the top. Don't forget to close that parentheses, very important. Then we hit divide, and what's in the bottom? Log of 1/2. And we get 3.015, somewhere around there, 3.015 half-lives. Now, if we look, though, we're not quite done with this problem because the problem did not ask how many half-lives have gone by. The problem asked, how many years will this take? So we've got one more simple step. If I know that each half-life is 12.33 years, and I know that 3.015 half-lives have gone by, all I need to do is some simple multiplication to find my answer. It will take 37.2 years for 3 grams of tritium to decay to 0.371 grams of tritium. So, when you have a fractional number of half-lives, these two equations can help you out. But if you have a whole number of half-lives, you can do it the simple method. Good luck.